Hey everyone, in this video I'm going to go through questions 31 through 36 of the USNCO 2025 local exam. This is the equilibrium part of the test, and you can follow along with both the exam and the solutions document I've written in the description below. So let's begin with question 31. I'm actually going to start with the second statement first and go to the first statement just because it's easier to explain, but the question is asking which of the below two statements must be correct at equilibrium. So II has to be correct because the whole point of equilibrium is that neither the forward or the reverse reaction proceeds. So if that's the case, the rates, of course, must be equal because neither reaction is proceeding. So II is going to be correct. And now let's go to I. So if we have a general reaction, A goes to B, just a simple reaction. Since we've established the rates are equal, let's say this has rate constant K1 for A to B, and then B to A has rate constant K-1. We have K1A must be equal to K-1B. And now it's not necessarily true that K1 equals K-1 because for the vast majority of reactions, A is not going to be equal to B. At equilibrium, it's not necessary that the concentrations of the reactants and the concentrations of the products have to be the same. So if A is not equal to B, then K1 is not going to be equal to K-1. So I is not going to be true, and our answer is going to be B. Now moving on to question 32, all you need to know for this question is the regular K form, or KEQ form. So for a reaction A plus B goes to C plus D, we have K equals the concentration of C raised to its coefficient times the concentration of D raised to its coefficient over the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. So I guess I should add here, this is AA plus BB plus CC plus DD. So essentially we have this reaction right here, A, B, C, D. So all we need to do is plug this in to our K form. However, there's one important exception here, and that's that pure solids and liquids aren't included in the K expression. So we just cross this out entirely. Now, all we do is plug in this to our numerator here, this to our denominator, numerator again, this to our denominator, and this to the power of 2. So doing all that, we just plug that in, see which form matches that, and that's going to be D. If you notice, this is C, this is D, they're both raised to the power of 1, and this is B raised to the power of its coefficient 2. Okay, moving on to question 33. This is asking which species is going to be most abundant at pH equals 11.5 for phosphoric acid. Just to clarify, that's H3PO4 here. That's not our answer, but that's just what phosphoric acid is. So if you're familiar with chemistry, you might know that when pH is greater than pKa, that the pKa of that dissociation, or rather the I dissociation, is going to be favored. So in this case, since the pH is 11.5, that's going to be greater than pKa1 and pKa2, but not pKa3. So the most favored form, or the most abundant form of phosphoric acid is going to be it after losing two H pluses, which is C. However, if you don't know this fact, you can actually just find it. Let's say that pH is greater than pKa. We can revert it back to its regular form because pH equals negative log H plus, and pKa is negative log Ka. We just take the negative log, not the negative ln. I made a mistake there. We take the negative log, and that actually flips the inequality. So H plus is going to be less than Ka, and this is a Ka form. So we just do that here. We divide both sides by H plus. So we get that this side is going to be greater than 1. So A minus is going to be greater than HA. And all that's saying is that it's gonna be preferred to dissociate into A minus and H plus compared to just staying in its regular acid form, HA. So the I dissociation is going to be preferred. So that's just proving why when pH is greater than pKa, that dissociation is favored. Okay, continuing with problem 34. This is an application of the Henderson-Hasselbalch equation because we're going to end up with the solution containing a weak base or a weak acid and its conjugate base. And let's break down how we get there. So let's go through every step of this problem. We have 0.900 moles of NaCH3CO2, and that's going to dissociate into Na plus and CH3CO2 minus. And we'll just ignore this Na plus. We don't need it for this problem. So there's going to be 0.9 moles of this. And we also have 0.5 moles of HCl, which is going to dissociate into H plus and Cl minus. Again, ignore the Cl minus. And we have 0.5 moles of H plus. So this H plus is going to protonate some, but not all, of this CH3CO2 minus. And that's where our weak acid and conjugate base comes from. So the two products of this protonation are going to be CH3CO2 for the stuff that it does protonate, and then we have the remaining anion from the stuff that does not protonate. And if you notice, this is a weak acid and its conjugate base. So we need to use the Henderson-Hasselbalch equation, and that's going to be right here. So we need to find the concentrations of this unprotonated CH3CO2 minus and then the protonated version of it. So let's break down how we get there. We have, again, 0.5 moles of H plus, and it's going to protonate exactly 0.5 moles of CH3CO2 minus. So that's going to be here. And then we have 2.5 liters of solution given in the problem. So we find this value for the molarity. And as for the unprotonated stuff, that's just going to be 0.9, our initial number for the number of moles of CH3CO2 minus the number of moles of protonated CH3CO2 minus, or HCH3CO2. So this is going to come out to 0.4 moles of that. We divide by the same liters value, and we get this for the molarity of A minus. Now, from here, we're given that the pKa of CH3COOH is 4.75. That's just this. I wrote it in a slightly different format. But yeah, that's going to be 4.75. So we have all the values we need to do this computation now. We plug in our pKa, our values for the concentration, and then we get this value for the pH of the solution, 4.65. And that's, in fact, going to be our answer. Now, let's go through question 35. So this, breaking down the question, is saying that there's a mixture of N2O4 and NO2, and it's at a given temperature. So we're going to increase the volume to 2 liters, and we're going to maintain the same temperature. So you might immediately recognize this as an application of Le Chatelier's principle. So let's break down what the reaction actually is. It's essentially this in equilibrium, and both of these are going to be gaseous. Sorry about that. So that's okay. This is a pretty bad arrow format. So we have 2 NO2 in equilibrium with N2O4, and these are both gaseous again. So according to Le Chatelier's principle, when you have an increase in volume, you have accordingly a decrease in pressure, and the equilibrium is going to shift towards the side with more moles of gas. So that's going to be the left side. So the equilibrium is going to shift left, and you're going to see more moles of NO2. So I is going to be correct. Now let's discuss why II is not correct, because we're going to need the number of moles to more than double when the volume doubles if the partial pressure is to go up. So even if all of this N2O4 disassociated into NO2, so it's all NO2, that's not going to cause an increase in the partial pressure. First of all, that scenario is not going to happen, but you're only going to produce 2 moles of this per mole of N2O4. So the actual increase in the number of moles of NO2 is going to be less than twofold. So the partial pressure can't more than double because, like I said, it's simply not possible. So the answer is going to be I only. Now for question 36, this is a KSP problem. So we're given a whole lot of values for the KSPs of these calcium salts, and we have the concentration of each of the anions being 0.05. So all we need to do here is write out the KSPs, and then from there we can just solve for the necessary calcium ion concentration, and then order that from lowest to highest, because that's the order in which the solids are going to precipitate. So you're going to get more of a feel for this problem as I just jump into it. So let's do that. Let's start with this first salt here. We simply just write out the KSP expression for that, and that's just shown here. We have our value here, and then we have our KSP expression. If you don't know what KSP is or how it's like expressed, you should look into that to understand this problem better. And we're just going to rearrange for the calcium ion concentration. We know that from the problem that the concentration of F minus, and in fact all of the anions in this question are going to be 0.05. So plugging that in, we get this value for the concentration of calcium ion needed to start the precipitation of calcium fluoride. Now we do the exact same thing for calcium carbonate. We have our value, we write the KSP expression, and we rearrange for the calcium ion concentration, and we get this. I'm not going to go over this one. It's the exact same process. We get this value. So the precipitation is going to start for the salt that needs the lowest concentration of calcium 2+, because the calcium ion is slowly being added to the solution. So we arrange this from lowest to highest, which is going to be this, then this, then this. So our order is this. And that's reflected in the answer choice B.